to have Gabriel Wittum from the University of Frankfurt with us this morning. He's going to talk about large-scale computing, and we're really interested to hear what you have to say. And please do remember this is an informal format, so do you ask your questions as we go. Sure. And please take it away. Thank you for coming.
Yeah, thanks a lot for the invitation to this very nice place. I enjoyed it, I think, last time in April, but I'm very happy to be here. It was difficult, you know, but I managed to be here, and I'm happy to talk about some things which may be interesting also for your community, though I'm not yet member of it. Yeah? So, an approach to large-scale computing. My background is high-performance computing, numerics, porous media, and also computing in biology. So, well, modeling. Dirac said about 90 years ago, the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are thus completely known, and the difficulty lies only in the fact that the application of these laws leads to equations that are too complex to be solved. Well, he thought of solving it on a piece of paper. Yeah? But we have other tools today. We are still not intelligent enough to do it on a piece of paper, but except maybe somebody here, but I refer to me. But we have other tools. We have computers, we have numerics, and so we may be able to bring this into that process. Basics of modeling. First, you need to model geometry. Geometry is a very complex thing. You may encounter this in geophysics, for example, but also in biology. You need material properties, and then you can model, based on that, you can model the processes, and you should always rely on first principles. Well, this is the Newton Institute, so on first principles. Every other thing is, to my taste, not a reliable model. Yeah? So you need the prognostic quality of the first principles. But note, a model is always an answer. It needs a question. Yeah? If I say yes, this is a positive statement, but if you don't know the question I answered with that, it's nothing. Yeah? So the model should be as detailed. You need an answer. You need a question. Otherwise, you cannot make a reasonable model. And related with that is a quote by Einstein: "The model should be as detailed as necessary to answer the question, and on the other hand, as simple as possible." Einstein said, man soll die Dinge so einfach machen wie möglich, aber nicht einfacher. You should make the things as simple as possible, but not simpler. Otherwise, you don't get the insight you need. Huh? And of course, there's a trade-off between complexity on one hand and reliability on the other hand. And more, the simulation technique is decisive for the complexity limit, which decides on what insight you can get by your model. So, we need a lot of disciplines. Modeling and simulation is an interdisciplinary effort. We start with a mathematical model. Typically, it's a system of differential and maybe differential and integral equations. There you need the people from the applications, geophysics in this audience, and you need mathematics, since the aim is to develop a mathematical object. This is a system of differential equations, so you will also need analysis to understand what you did there. Then you need numerics to approximate that. For unlike Dirac, we don't even try to formulate a solution on that level. We just do an approximate solution, and that's now the matter of numerics. So we need discretization, breaking things down to a grid or something like that, and finally ending up with solving linear equations. That's the only thing you can do. Also nonlinear equations, you do by Newton's method, so you reduce it to solving repeatedly linear equations. Of course, this means to do a lot of work, so you need to go to a computer, and that means in between this here is software, and this is now computer science. So you see geophysics, mathematics, computer science, and software, and of course the hardware will still show up. All this is so complicated since this here is a chain, and a chain is no stronger than its weakest link. If you are very good in modeling, but you are lacking numerics, you will have hard time to get an overall solution for your problem. The same holds true if you have a big computer, great at software, but you don't understand the models. Yeah. You may compute nonsense in no time. Huh? So you need to bring this together. So the first thing is the most complex one. It's mapping reality to mathematics. How do we describe reality, whatever this is, by mathematics? This is, of course, a difficult question. And the most difficult one, since from there on we are in the realm of math. We can talk about errors, everything can be quantified nicely. But here you always have a strong uncertainty. So numerics is about errors, and more errors are determined by complexity. Software tools is about complexity, flexibility, portability, maintainability, and other entities. And all this is so complex since hardware is the limiting resource. Yeah? You can build computers as large as possible, but you still are far from what you would need to describe everything in detail. So, yeah, we need an approach to access these complicated problems, even having in mind the largest computers you can get. But we need an approach which helps us to get these problems to these computers. The first thing is adaptivity, that is refine a grid where needed. That's a 5-spot problem from reservoir engineering. You have, think this is just a top view on a reservoir. Here you see oil reservoir, so think of this being sand soaked with oil. And you put an injection well here and an extraction well there. And you have, of course, varying conductivities here. So where you have red, you have a high conductivity. In the blue places, you have a low conductivity, and the rest is in between. So as soon as you start the process, you see the water is lurking here already. You inject water here and extract oil there, and then you will see what happens. I'm talking about adaptivity. So you see a front developing and marching through the domain until you have a breakthrough over here. And now, of course, you will just feed water from your extraction well, which makes not much sense, so you will stop the process. And you see about maybe 60% of the area has been, of the oil has been recovered, not more. And you see there was a front marching through the thing. The front, of course, is a very complicated thing. It's a kind of free boundary, and of course it's oriented and pinned by these initially given conductivities, hydraulic conductivities. And here you see the grid. If you looked at this, you see how the grid develops. You see the grid is refined just where the front is, since we want to have the front very precisely. Yeah? Here, on the oil side of the front, the grid is coarse. Behind the front, the grid is coarsened again, but not too coarse, since you need the front speed right. Okay, the same thing can be done in 3D, of course. You see here, there are very big prisms, and they are refined when the front comes through. You have injection here, extraction there. You have very big cubes, and you see how it's refined and coarsened again after the front. So, adaptivity will be one of the key ingredients, which helps us to reduce the number of unknowns we need to the places where they actually are needed. For all the interesting problems are not smooth, having a solution behaving all over the same, but they have critical areas. They really want to know what happens. Yeah? Then, the next thing I mentioned already, complexity is decisive. There is what I call the HPC paradoxon. Look at algorithm complexity and think you are the boss of a big computer center which owns one of the largest computers in the world. So you have a lot of algorithms running on your computer, and there is one algorithm with execution time depending on n to the q. N is, in our context, the number of unknowns, but can be some size determining parameter, and the q should be larger than 1. That is, the algorithm is non-optimal. Yeah? So if you buy a new computer, that is on a new, larger and faster computer, larger problems will be computed. You will not use a big parallel computer just to compute 2 plus 2. You will do more on it. So assume the new computer is a factor of alpha larger than 1, faster and larger than the old one. To compute a problem of size alpha times n, this is the corresponding larger problem, the new computer needs a time of, just plug this in here, alpha to the q times n to the q. This means alpha to the q minus 1 times alpha epsilon, alpha e. E was the time, execution time for the original problem on the old computer. Alpha e, since the new computer is a factor alpha larger, this is just exactly the same time you did the original problem on the old computer, but now you have an additional factor alpha to the q minus 1, and this means the larger and faster, the larger alpha is, the larger and faster your new computer becomes, the longer the execution time will be. Even if you invest billions, this will not help. This is mathematics. Yeah? So, and large-scale computing means, of course, large-scale computing really needs optimal complexity algorithms. Otherwise, you don't have a chance. Yeah? You will run into that problem if you don't use optimal order algorithms. So we need optimal order algorithms. In our case, this is a multi-grid method using starting from coarse grids and going to finer and finer grids, which are adaptively refined and so on. We need, of course, parallelism. Even an iPhone today is a parallel computer. And we need adaptivity, as shown, in order to reduce the complexity as far as possible. You can also use higher order functions, but since the critical part typically is non-smooth of the problem, it's not so much going higher order, which is of my interest, but going to local grid refinement. So, and bringing these three steps, these three issues together, yeah, adaptivity, parallelism, and multi-grid methods, we started 25 years ago to develop a program package, a software package called UG, Unstructured Grids, which is able to solve a system of PDE on unstructured grids. That's it. Yeah? This is not so easy to do that, since parallelism, you typically distribute your grid on your computers, and adaptivity means you change the grid all the time. This is a thing which really has to be well balanced. Otherwise, you get in trouble. Multi-grid makes the thing even more complicated, since you do not have just one grid, you have a hierarchy of grids, and all this needs to be done efficiently. In the long time, we are working with this package and continue development of that package. We solved a lot of problems in computational fluid dynamics, turbulence, for example, large eddy simulation. We did multi-phase flow, combustion, aeroacoustics, flows with particles in porous media, just the porous media flow, then fractured media. I will talk about this today. Thermohaline flow. We did transport and reaction. We also worked in electromagnetics, doing eddy current models and multi-scale models for eddy current models. In mechanics, we just finished a project with Porsche and Daimler on crash simulation, on robust crash simulation. See, it's all the same. It's all mechanics finally. It's all Newton's ideas. Yeah. Then in energy research, we look for aeroacoustics from wind turbines. We are working currently on biomass and biogas production, reservoir engineering, combustion, process engineering. We did mixing, extraction, crystallization, environmental problems, as I said, groundwater flow, thermohaline flow, but also waste disposals. In biology and medicine, we are still working on pharmacy, on transdermal drug delivery, which is a very, very interesting topic. We looked in tumor growth, in the growth of sclerotic lesions, and we are in this human brain project where we are working on signal processing in neurons. And there you have a lot of different different and very, very challenging problems. Then we also worked in finance. Yeah. So here are some results. This is a thermohaline flow. You will see a bit later in the talk. This is a a large eddy simulation of a flow past a static mixer. Here you have the profile of the mixer, and the flow is coming from the left going to the right, and you see the turbulence developing here. This is the bending of a part of a car body. Yeah. This is induction heating of a pot of water. Yeah. It was interesting. We cooperated with an industry company which claims to be leading in producing these induction heaters, and they didn't know where the largest where the largest heat is induced. Yeah? So we computed that, and they always thought the largest heat is in the middle. No, it's in the ring. Yeah? It's in the ring. This is the bottom of your pot, filled with water. It's up here, and this is the induction heater. And there you see the arrows show the electromagnetic field. This is skin, a model of transdermal drug delivery. Here you see the so-called, what we call a sponge effect of the skin, but we'll see this later. And this is from neuroscience, signal processing on a number of neurons just connected together with some synapses. And here you see the how a 3D model tells you how the field develops. So for all these things, this code is the core tool. It includes about 140 person years for development by now. We started the new version, the fourth version, when I went to Frankfurt 8 years ago. Here are some names. And so UG4 compared with the older versions is a completely new code. It's strongly modularized. We use hybrid unstructured grids with hanging nodes, finite volumes of arbitrary order, finite elements. We have parallel, adaptive, and robust multigrid methods. The code is highly scalable, as I will show you in a minute. And we also have what we call filtering algebraic multigrid as a separate module. So you can even take it out of that code and put it in yours. And this is independently parallelized. The grids are hybrid unstructured, so you can combine triangles, quadrilaterals in a free way. In 3D, of course, cuboids or hexahedra, tetrahedra, pyramids, prisms, all this is feasible. The closure is done by so-called hanging nodes, that is by interpolation finally. And there is, Sebastian Reiter finished a very nice tool for generating and handling geometry in grids. This is independently available, and all this is free, by the way. So it's a really great thing to work with that. For setting up a domain and generating the grids and so on is a real headache if you did it for a real application. It's always independent of the grid, as I said, and the parallelization. You have an efficient parallel data migration via MPI-based parallel communication layer, also done by Sebastian Reiter, and which is a new thing also, we have a graphical user interface based on a new library called Virtual Reflection Library, written by Michael Hofer. They look like that. You have the chance to input some parameters and finally to say run. But at the same time you see the results, and so on. And well, this is just a graphical user interface, but the great thing with that graphical user interface is that it's automatically generated. You don't need to waste PhD students' power to produce that. So this is used. It uses the tool. The VRL uses Java reflection. In Java, you can analyze the code. So as soon as a command is made available, somebody wrote something and it produces. Finally, you will produce a command. So to access this from a scripting area. But as soon as this is available, you can analyze what's the input, what's the output. You can generate a graphical user interface, and no maintenance is necessary since it's automatically adapting if you change the code. And you can do workflow control. You can zoom in, zoom out. You can really, on a very high level, devise your model, your simulation, and then you can also zoom inside and define all the parameters you need for your smoothers or something like that. Yeah? And the tool is independent of UG, so can be used independently. By the way, all these codes are available via GitHub under LGPL, so you can directly access it. PCL, this is the parallel communication layer. What does this do? Well, you need this as a communication library on a parallel computer. You need to group objects into interfaces. Interfaces connect groups of elements on a different process, on different processes, and the interface are grouped in layouts. Communication can be scheduled for interfaces and layouts. It's finally a template library for point-to-point communication between abstract object sets. It's highly adaptable to different graph structures. So forget about 2D, 3D. It's just living on graphs. Yeah? It has a minimum storage overhead, and only references to interface objects are stored, so not the objects themselves. And the identification of objects is done through local order in the process interfaces. Usually, and I think we never required up to now global IDs. Global IDs, of course, this would solve the problem of this is element number that and that on processor N, and this is element number Q on processor P. So how do they communicate? How do they identify each other? But if you do it in an intelligent way, you can save the globalization. Globalization actually damages complexity, since you easily get search processes which are not of O of n. So you want to avoid globalization. And this is a computer science problem, but you run in all these problems wanting to solve to compute solutions of your models on large-scale computers. UG3, this was our first three-dimensional code. It was finished in '98. And the parallelization was based on a special tool, dynamic distributed data, but this was not O of n. There we had this problem with the global IDs. We had a strongly limited parallelization up to about 4,000 cores. Now UG4, based on PCL, gives a perfect scaling up to, this is the largest computer we were able to access, 264,000 cores. Well, here you see that, the scaling, if you go from one processor, solving the Laplacian in 3D with a geometric multigrid on a structured grid. This is the computer, all this was done, this is the large one in Jülich. We need, with 60,000 unknowns, we need about 7 seconds, all over, from the start of the job until the end. Then we increase this, we increase the number of processors, and at the same time we increase the problem. This is weak scaling. Yeah? Doesn't make sense to run a problem with 60,000 unknowns on 262,000 processors. It's very simple. Yeah? So we increase this, and we end up with some of about 20 billion unknowns here, and the time increases just by about 10%. I think it's a bit worse than 10%. It's this was 7 seconds, and this is 7.8 seconds. But that means that you solve the big problem at almost the same expense as almost the same time as you solve the small problem. This makes it feasible to do large-scale computing. This does not hold only for Laplacian. This is now 3D uniform computation of linear elastic problem, as you can see here. And here you see the number of unknowns increasing from 14,000 to 3 billion, and going from 1 core to 262,000 cores, which gives you an acceleration of 234,000 and an efficiency around 90%. So, and now I want to come a bit closer to what the community is interested in. I want to talk about modeling computation of thermohaline groundwater flows. But feel free to ask questions. Yeah? This is an open session. So, please. I've been given 2 hours, way too much for what I want to say. Yeah. So please feel free. Yeah.
Quick one. How much? So you showed 2 examples for scaling. I was wondering how much that changes for problems that might have wildly varying coefficients. Does the scaling hold up independent of the mathematical problem, or is there some limits to what the solvers can do?
Well, the main problem when you go to more advanced models, they are typically nonlinear, and you can't do that scaling since on the different grids you have different behaviors of nonlinearities. But I will show you, just in that context, I will show you a scaling for such a problem, which is highly nonlinear. It works. It doesn't give this 90%. We end up with about 70%. But of course, this can be completely different if you have a different nonlinearity. Since you compare different problems on different grids, you increase the number of unknowns. That means you increase the problem size. So you also change the nonlinearity in the discrete level. Not on the asymptotic, on the continuous level, but on the discrete level, the nonlinear behavior might change, and you really see that. This influences the spectrum of the matrices, the spectra of the matrices you have, and of course the solvers behave completely different, so you cannot easily compare that. That's why I always go to that simple problems, but I will show you some more involved problems later. But this is a good question, thank you. So, thermohaline flows. Let's start with density-driven flows, density-driven groundwater flows. They are interesting for people living on the seaside, for example in the Netherlands, where you have, also here of course, where you have saltwater intrusion into the aquifers, and of course you don't want to get salt water from your water tap, you want to have fresh water. So it's an interesting question, where is the fresh water, where is the salt water? Just in a project together with East Frisian Waterworks in northern Germany, and they have such a problem, but they have a lot of saltwater intrusion, and how do they need to pump that they can do a sustainable water economy there. In upconing, in arid regions, for example, you may use groundwater heavily, you pump from below, and of course on top of this groundwater you have the fresh water, and the farther you go down, the more brines you will have, the more things will be dissolved in the water. And you only want the fresh water coming up, so you need some strategy here. And the reason why we started this project also a long time ago, this was to find something about the flow, to be able to compute the flow around a salt dome. Salt dome is such a diapir coming up due to density difference. The salt typically is less dense than the mountains, than the rocks around. So what happens here is just the opposite of a droplet dripping down. It comes up, but you should know that. And it's interesting to ask if you have some, so use this as a deposit for nuclear waste, for example. You may have that some nuclides or something, some contaminants somehow manage to escape the salt dome, and then where do they go? Do they just go down? You may have a convection roll developing due to density. This is not a potential flow anymore. And do they go down, which people would like, or may they even go up again? So does the salt water come to the surface, to the ground, where you recover the groundwater or not? And you need to do this by a simulation, typically for at least 100,000 years, since nuclides are very long time stable. Not all, but there are enough of them. So the model is comparable to what you know. This is a kind of modified Darcy. This is a kind of, this is the pressure equation, let's say that way. The V, the velocity, is given by a modified Darcy law. We have to consider that the density is not constant. It depends on the concentration. And you have a second equation for the concentration here, which is nonlinear, and also nonlinear by this here, by this diffusion tensor, dispersion tensor. There we use the full Scheidegger tensor. Yeah? So you see you have a lot of nonlinearities in here. And of course this is not comparably simple to the Laplacian or something like that. Though the Laplacian is one of the main difficulties to overcome here. So here is the density and C is the concentration. So you have the two coupled equation to be solved.
So, quick question about notation. Your symbol N, is that porosity or?
Let me see.
Symbol N in front of the rho mean?
Yeah, this will be porosity in that place. Yeah. Okay, may change in the course of the lecture, sorry. So, this is, you know, in geophysics or in geohydraulics, you have very, very flat domains, so this is extended by a factor of 100 in the C direction, in the Z direction. And here you see these are 7 layers. There is the salt dome, and there we have some total of 7-layered model around it. You see the salt rising from the salt dome. Just go back again. See how the plume rises from the salt dome. Okay. This is a topic for large-scale computation. And this was the first thing we did in fully parallel adaptive mode. You see how the grid is refined in the course of the simulation, and how this is the grid, how the plume develops. In this case, we got a plume which really reaches the surface here, which people do not like. And here you see the change of the load distribution on the load balancing of on your parallel machine. 2D, 3D, the same happens, but harder to visualize. So this is an old sheet coming from more than 10 years ago. So there we were able, the results have been obtained, I think, in 2000. There we were able to go to 512 CPU, 66 million unknowns, not much for us today, but at these times this was quite okay. And so we got an efficiency of the adaptive refinement, of the adaptive parallel process of more than 50%. And the adaptive refinement here, this was with the old communication library, which did not scale. No? So, and the adaptive refinement really shows that adaptivity, the main time is spent in the solvers. The adaptivity and the load migration is comparably small compared with the solving time. So the solver is still the decisive thing. You have to do multigrid. Well, this has been published long ago, and now with UG4, with a new code, a new calculation, this is the so-called elder problem. Yeah? You have the salt dome up here. This is initially filled with fresh water, and then due to gravity, fingers develop, and you see them coming from about 5 down to mainly 1. We didn't really see the 1. We saw 1 plus very small child. But here you have 5, and now the 3 and these 3 join to form 1 big finger. And this is now a comparison starting with 32 cores, 2 billion degrees of freedom, 11 iterations. This is just for the first time step here. 11 iterations.
Of what? Iterations of what?
This is of the linear solver.
So how are you solving the nonlinear problem?
Well, this is in this case, no, maybe this, let me see. No, I think this is, this is a Newton. In this case, it's a Newton's method. We are just experimenting with doing a Limex method, that is combining a nonlinear iteration with a time stepping. Yeah? So to if you know this, linear implicit methods with extrapolation. They have been introduced in the 80s by Teufelhardt, for ODEs. And that's, then you do more steps on the equation, but less time steps. Yeah? No, the other way around. You do more time steps, but less iteration steps of the nonlinear problem. Yeah? That's the way. Yeah? And I think I don't have these results. But maybe we can discuss this later. I should have the results in here, but not in the talk. But we can discuss this. You see, this is the scaling going from 32 to 131,000 cores. So 8.5 billion unknowns, and we reach an efficiency of 71%. This is still quite nice, and you see the number of iterations. This is the number of linear iterations, I think. So it will be one step of the Newton's method. And what is interesting here, you see that the number of iterations even falls. Yeah? This sounds crazy, but for highly nonlinear problems, you cannot prove anything mathematically, in particular for that problem. Yeah? I don't know anybody who would be able to do that, prove convergence of a nonlinear method for that, yeah? Without unreasonable assumptions. Yeah? So what you have is only physics exists. If our model describes the reality sufficiently good, yeah? Then we are close to a solution. And that means the finer our grid becomes, the better we resolve the nonlinearity. Yeah? This is, in particular, for solving nonlinear problems, this is a very important thing. Doing fine grids for such nonlinear problems is not only to reduce the discretization error in the linear sense, that you get a better resolution of the differential operators, but also to get a better representation of the nonlinearity. And since you do not have mathematical access to the how to solve the nonlinear problems with your means you have, with your computer you have, then you really need to rely that the nonlinearity is reasonably represented. And that's the thing I often see, that if you refine the grid, the thing gets better. This is exactly, I explain it to my students with my horse. If I go away from the stable, the horse is slow. As soon as I turn it, and it goes home again, and the closer it comes to the stable, to the home, the faster it starts to go. Yeah, it senses the solution, like these problems here. The nonlinear methods, if you have a reasonable representation of nonlinearity, they find the physical solution. Okay, then there is a second part to it called R3T. This is a package for solving systems of up to 160 coupled convection diffusion reaction equations in 3D. This is, of course, a model complexity, which is very hard to handle for the modeler. 160 equations. What do you want? What do you see? Yeah? What are you interested in? Yeah? But you know, you start with radioactive decay, always new species are produced and so on, so it's not so easy. So we have radionuclides, and the name comes from radionuclides, reactions, retardation, and transport. This has been extensively validated. We had especially designed experiments, the so-called salt pool experiment, with a very interesting example, very interesting result showing that modeling, asymptotic modeling, is often not able to describe the experiment was a cube of 30 centimeters edge length, and there the asymptotics for the dispersion tensor we used, this is Scheidegger tensor, was apparently not given. So we always had problems to find the right frame-independent parameters. Then also field cases measured had been done. This was in Cape Cod. There are a lot of measurements of a contaminant case. So we did extensive validation, and we extended it to thermohaline flow, so adding temperature. This gets more in the direction of geophysics, not staying on the surface. Then also looking for fractured medium. Adding temperature means we need another equation. Things get more involved here, you see that. So theta is the temperature, I think. And so you have the so-called Onsager relations, and these are the fluxes and so on. Everything gets very involved. Then we solve this, we set up our code to solve this problem, and we studied some interesting effects. There are well-known Ludwig-Soré effect. That is, you have, in general, you have the opposite effect of temperature and salt concentration. Higher salt concentration means the thing goes down. Yeah? Higher temperature means the thing goes up. And now, of course, the situation depends who wins. Yeah? So there are two well-known effects. The Ludwig-Soré effect is the connection of mass flux with temperature, with a temperature gradient, and the Dufour effect is the connection of heat flux with the concentration of the gradient. And we generalized this moving particle problem. Oldenburg and Pruss introduced in 1999. This was in 2D. We did this in 3D. You see negative buoyancy. This is the Dufour effect. Yeah? So the salt concentration wins, goes down. You see all these fingers, but the number of fingers strongly depend on your grid and the grid refinement. There are several solutions possible. Positive buoyancy just goes the other way around. Here we have that the mass flux is connected with the temperature and goes up. Yeah? This depends on the adjustment of the initial parameters, and of course of the conductivities and so on. But as I said, symmetry, you see a symmetry, after some time you see a symmetry breaking due to grid refinement. So never believe, if you computed a certain number of fingers in these unstable problems, never just believe that. This is true and publish it. This is done quite often. But be critical, compute another grid, and you will see what happens. Typically, due to the instability, the instability is just stabilized by the grid size. So if you change the grid size, you get another number of fingers here. And you see a symmetry breaking. So this was about turmoil line flows. Now let me come to fractured medium. Fractured media happens quite often in rock, typically. Granite, you have a lot of fractures, fissures, and so on. And since granite is considered as a medium to place a nuclear waste disposal, the first one is actually starting operation soon. This is in Finland, right on the coast. Sweden is next. Sure, come. But you have a lot of fractures in the granite. Granite itself is quite impermeable, as you know, but you have these fractures, so it's still wet inside. Here, this is a model from Espö, from the Swedish rock lab on the island of Espö. Here they have an old mine. They have a mine, and these are the mine tunnels. And from there, they found a lot of fractures, you just can see here. Typically, to solve such a problem, you do a low-dimensional formulation in the fractures. This is well known. You reduce the whole thing to the fractures. But if the fractures are not the only pathway you have there, but you also have that the material itself may transport, so slowly, but transport a bit of the stuff, then you have to compute the full domain. And then you can use for the fractures a lower dimensional formulation. This has been done for the multi-phase flow by Helmich, Kolditz, Reichenberger, and other people. And of course, it's again a matter of multi-scale modeling, since they have fractures of very different size and dimension. So the question is, can we use a low-dimensional formulation for a fracture, and is this justified, and when is it justified? So we can use a low-dimensional formulation, we can use a full-dimensional formulation. And the representation of fractures is polyhedral faces plus pointwise thickness. This is that here. And then we come from here to here by expanding to a volume. Here, extrusion of a triangle and quadrilateral, and you see coming from here, from this fracture representation to that, is just by expansion. You may run in trouble when you have an intersection of fractures, and then you have to think that it gets right. Well, we also have, in the density-driven flow model, we have to average across the fracture. Yeah? That is, we build this integral, epsilon is the fracture thickness. Yeah? So we integrate across the fracture our functions, and of course have to build the average of that. And the difficulty now is to find the transmission conditions. How do you fit the equations in the different domains to match each other? That's difficult, since in the lower dimensional representation, the unknowns get discontinuous. So what we found is, the first thing you have in the full dimensional is easy. You have continuity of normal fluxes and continuity of pressure and concentration. But not so in the low dimensional model. Now, in the low dimensional model, these things are no longer given. The flux may be, but not the continuity of the fields. And Alfio Grillo found, one of my former associates, who is now professor in Italy, he found that the auxiliary vector fields, Q alpha and P alpha, these are Darcy velocities and fluxes. Yeah? If you formulate it that way, these vector fields, Q alpha and P alpha, are continuous across the interfaces, and that's your transmission condition. So, you see, epsilon is the thickness of the fracture. So you end up with this kind of model. Looks quite complicated. I don't go into detail here. And then we set up and looked for, that's this up, and looked for Henry's problem in 2D. This is intrusion of salt water into a freshwater aquifer. Yeah, this is the aquifer. These are the boundary conditions. Here you have full salt concentration. Here you have fresh water. And now this starts to intrude here. And you have some fractures. There are more parameters, so everything has to be done very precisely.
Where is the fraction in that?
Yeah, there are several fractures. I'll show you in a minute. We changed it. This is, of course, the main question. But since we did several configurations, these are the general parameters. And now you have a fracture down here. This is the easiest thing. The fracture is 3 millimeters. This is 1 meter high and 2 meters wide. So the fracture is really a fracture, a very small one. Now you start the computation. You see where the fracture is. You get a profile. You get a stronger input. I think the fracture is about a factor 10 to the 3 more permeable than the surrounding rocks. So in the low dimensional representation, this looks fairly the same here, and actually both curves, this is the behavior in over time, this is time, and this is the concentration in this point. Both curves exactly fit each other. So lower dimensional representation is fully justified. Then we did a number of other configurations. This was the one here. There, I even don't see the fracture. I think this is without fracture. And here you have a fracture over here, and here you have 2 crossing fractures. Yeah? So you see the fracture finally determines the flow. Then we widen the fracture a bit. We just tested, is there a critical size from which on you should not use a lower dimensional representation, and why? So we widened it, and with 24 millimeters, initially it was 3 millimeters, then you get quite a different profile compared in the lower dimensional representation compared with the full dimensional representation. Here, this is not good to see in the projection, but you have a substantial error here. Why? we tried two things. First we kept the size of the fracture fixed and changed and varied the conductivities. Varying the conductivities doesn't give you much information. So it's not about the conductivities in the fracture. But if you just keep the conductivity fixed and vary the size of the fracture, the thickness of the fracture, going from 0.006 up to 0.018, yeah? So this is a factor of 3 here, yeah? This part. There you always have a behavior with the absolute error of the concentration. Error always means compare with the full dimensional model. Yeah? You see all this is okay. Yeah? Change is not large. But going from 0.018 to 0.024, yeah? You have a big jump here. Something is coming up. Why? And it was interesting to study the physics a bit, to look a bit closer into the fracture and what happens there. Here, this is for the thin fracture. You see the profile inside the fracture develops as you expected. This is, of course, the full dimensional computation. But if you go to a thicker fracture, you see the thing starts to develop convection rolls. You have a rotational flow inside the fracture, which you cannot resolve by a lower dimensional model, of course. So you have definitely a different physics. If you get rotational flow, you should look for vorticity. So you look for the curl of the velocity, this is that here, and find that the vorticity is maximum if the concentration gradient is perpendicular to gravity. So gravity and the concentration gradient that way, then you have the strongest drive for such a rotational flow, which is in the case in our configuration. We did this in 3D too. Of course, great, but you see how it's meant and how the fracture has been done. And here you see this is the full dimensional thing, and this is the lower dimensional representation. The lower dimensional representation is fine comparing these two pictures, but not comparing these here. So this tongue is very, very precise and very narrow up here. You even have some side effects. Yeah? Here you don't have this. This is like looking for an upwind, simple upwind discretization for a high convection. This is unprecise. Yeah? And this is not unprecise due to the grid size. It's unprecise due to the wrong model. Yeah? So here again, this is full dimensional, and here looking inside these fractures in 3D, you see this rotational flow developing. So the observations is for very thin fractures, a low dimensional model suffices. In wider fractures, rotational flow can occur. The question is, can you quantify that? How do you quantify that? Yeah, you look for the quotient of the flow along the fracture and the rotational flow, this here. So we define a theta f, a number, which just relates the flow velocity in the fracture, along the fracture, with a rotational flow velocity. And the rotational flow velocity can be computed by this here. This is the curl of the Darcy velocity. This is the quotient of the fractions. This is salt mass fraction, and this is a kind of base fraction you refer to, and this is the quotient of the two conductivities in the fracture and in the matrix, and this is the thickness of the fracture. So this is the rotational flow velocity. Theta f is dimensionless. It characterizes the flow in the fracture, and if qf is larger than q rod, the rotational flow can be neglected if this dominates and this is small. But as soon as q rod gets large, yeah, then you really have to do the full dimensional problem. So if theta f This is the maximum of all these theta small f and all these elements in the fracture. Yeah? This is smaller than 1 minus delta, then you have to go d-dimensional. Delta is a parameter you have to adjust. And if it's larger than 1 plus delta, you can go d minus 1 dimensional. So the fracture representation, and then we do a dimensional adaptive computation. The fracture representation is adapted during the computation, and the full dimensional resolution is used only if necessary. Yeah? So normally we want to use the lower dimensional representation since it's much faster. But if it's not reliable, we have to switch. Yeah? So that means that numerics get a bit complicated. You need two grids, one low dimensional, one full dimensional. You need transfer operators between these grids, so you need to be able to transfer functions from the full to the low dimensional and vice versa. And you need a criterion when to use which formulation. And the criterion is exactly this compute theta f, and then you can switch. If it's larger than 1, you do the low dimensional. If it's smaller than 1, you do the full dimensional. And here you see the comparison. For that problem, here is the fracture. And you see this is the d-dimensional, this is the lower dimensional representation. Here is the jump in the salt mass fraction. Yeah? Here is time, and you see that the height of the jump is quite different if you do the full dimensional or if you do the lower dimensional problem. This is the relative error here. And the dimensional adaptive thing is, well, it's the green curve. The black one is the full dimensional one. You get a small change when you go to the, when theta f is larger than 1, you come to that curve. But the critical part is reported correctly, and then this is calculated still in a reasonable, as a reasonable approximation. The same in 3D with small fractures, no problem. With large fractures, you see very different behavior between the full dimensional and the lower dimensional formulation. And there we finally did, to assure this, we finally did some, I think, 1250 simulations on a stochastically constructed situation. So we vary thickness and length of fracture, the angle with the gravity, and the parameters like conductivity, etc., and the boundary conditions. And for each configuration, we did 3 simulation runs: d-dimensional, d-minus 1 dimensional, and the dimensional adaptive one. And of course, the d-dimensional is the reference solution, and we always computed the maximum relative error. And then you see the following. If you have, well, let's look for this here. I don't know what. Yeah. So this is the d-minus 1 dimensional representation, the low dimensional representation, which is wrong, which is good. That error larger, smaller than 10% in about 65–60% of the cases, but in a significant number of cases, it will report nonsense. Yeah? So if we do it with a dimensional adaptive method, you see there is no case with an error of larger than 40%. Yeah, I think that's it. So thank you for this time. If you want, I can continue after a break, but we can also make full stop here. This depends on you. Thank you for your attention.
Thank you very much. Let's open this up for questions. Yeah, Jonathan.
So I think it's about 3/4 of the way through the presentation you had the like a cube of fluid, and you're saying the adaptive mesh could change how many fingers you saw appearing. Mm-hmm. I noticed in those models the fingers always started at the corners, and I was wondering if that could be to do with how the adaptive grid responds to corners to generate the initial fingering there.
Well, so the grid size in general on an unstable problem, the grid size may stabilize the instability. Yeah? So if you change the grid size, you get a different solution. Yeah? For the unstabilized case has even an infinite number of solutions. Yeah? So no matter if you do adaptive refinement or not, yeah, this must be clear. Yeah? If this is not clear, you will, and actually just in this case of density-driven flow, we have a number of papers of that type. That people computed this solution for the elder problem, claiming on a new grid, on a finer grid typically, yeah, claiming, oh, this is, we get a solution with 5 fingers or with even 8 fingers. This is the solution now. Yeah? There are, looking over the history of the last 30 years, 40 years, yeah, you really see these papers coming up. This is just nonsense, since they didn't understand that the problem finally, starting from the initial point, has an infinite number of solutions. And it just depends on the way you start the computations and so on, so mainly on the grid, what number of fingers you get out. Yeah? So this is the first thing. And of course, if you do adaptive refinement on that, yeah, it will not help you. Yeah? It will get a solution faster, but it will change the solution. But breeding always may change the thing if it stabilizes. Yeah? Does this answer your question?
So,
Sorry, there was the next question coming, unless you had an immediate follow-up.
The immediate follow-up is there's two sides to the problem in terms of how many fingers you get, which is sort of a quantitative solution versus the qualitative side of where the first instability comes. And I was wondering whether the process of adaptive refinement could be promoting the first instability that leads to the drop down being at the corners of the initial fluid or not.
This is some time ago, but we once did a project with Wolfgang Tietzelbach on exactly that topic, with his fingers in that problem. And he thought that he's able to pin the number of fingers by introducing heterogeneities into the problem. So he wanted to do an experiment. Yeah? So have some high conductivity regions, which of course naively you think there the finger will develop, and in the other parts not, and then you get the problem stabilized. And he had a very clever PhD student who was able to prove that this is not the case. So this thing is unstable with these equations and stays unstable. So what you do when you do the computations, you stabilize by the way you compute. First by your approximation, which is mainly determined by the grid, but also the discretization. If you take another discretization, they also contribute. Yeah? And also where you also the round-off error in your the truncation error in your computation, yeah, may play a role. Yeah? You know this from bifurcation problems, where you really have to get around that. If you want to be very close, you have to make the influence of the round-off error clear, of your arithmetical error. So now you can ask, why didn't you show us on what grids you did that? Sorry, this is my fault. Yeah? I can look it up, but I don't have it with me. Yeah?
So is that question selective?
yeah.
Good.
Okay.
Have you looked at the case of water infiltrating a dry soil? There you also get fingers.
Richard's equation. Yeah.
And whether the kind of issues that you encounter with density-dependent flow also occurs there, whether you will get different number of fingers with lower coarser grids and finer grids will disappear or not.
No, we didn't do that yet. We worked on Richard's equations, but it's some years ago, and we didn't look for that issue. Yeah? But this could be done. Yeah? That's a good idea.
In your discussion of the fracture flow, when you went to the full dimensional description of the flow in the fracture, were you using there in the fracture, were you using Darcy or Stokes?
This is Darcy.
It's all Darcy.
We assume that the fracture is filled with some sand, some material.
Some debris.
Yeah, some debris typically. Yeah. So we just have two different conductivities. Yeah. Where is the?
That I understand. So when you compute, but then you were comparing the rotation of the velocity, which is a gradient.
finally, you compute the rotation, the rotational part of the velocity. Yeah, where is it here? Yeah. So the vorticity. Yeah, as you do in turbulence. Or it's a kind of, it's not turbulence, but it's somehow similar. Yeah? And it's interesting for. I don't know if this ever has been described, this effect. It's natural somehow, but people doing these fracture simulations never came to that point.
Next question, Prof.
Since a few previous days we were discussing coupled hydromechanical problems.
Yeah.
So do you think it would be possible in your computational framework to try to model both fracture propagation, for example, and fluid flow through the fracture?
Sure. Fractures here are static up to now, since this is what we have found it for. Yeah. Finally, you can't demand everything from your PhD students. But it's no problem, since we have in this code, we have a mechanics part too. Yeah? And we even introduced some new solvers for more complex nonlinear mechanics problems. This is usually, if you do elastoplastic problems, you usually use the Seymour-Taylor back projection algorithm. Yeah? But this limits your the dependency of your strain tensor, yeah, on the deformation, yeah, to very special nonlinearity. And if you have more complex nonlinearities, this does not work anymore. So we set up a new solver which works also for more complex nonlinearities, which we use in biomechanics. Yeah. So up to now, this is the same code basis. Up to now, there is this hydromechanics applications, and there are the nonlinear mechanics applications like crash computations. And well, it's just almost trivial, but that needs to be done to join this. But you need a model for the fracture propagation. Yeah? How do you model fracture propagation? Yeah? Fracture tip, how does it move?
Yeah, but hopefully this should be a spontaneous outcome of your constitutive relationship. So if you have like hydromechanical model for fracture propagation, and potentially, since you do this crash experiment, so large deformation is not a problem, right?
This is not, depending on, but we did large deformations, but large deformations is not trivial. But if you see how this is done in practice, and industry is heavily relying on these codes, then you can, this is incredible. You can just shake your head. People do models derived from mass conservation, and if you take a standard code, which is used all over in car making industry, and take such a beam, steel beam, before a crash it. Before the crash, it has 750 grams weight, and after the crash, the code will report you 1 kilogram.
Wow.
It's an inverse nuclear reactor. Yeah? Well, they just do not differentiate between damping and changing the mass. But that's the level at what these computations are done. And I think there we can do better, I'm sure.
So it's very difficult to parallelize in time.
Oh.
Could you comment on how you handle time?
Well, in these computations, the time was sequential, but you can parallelize in time. We have a project ongoing, and we have some publication on that. Yeah, the first thing, this is together with Rolf Krause from Lugano. The first thing was to use parareal. But parareal, this just means that you add some parallelism at the expense of doing more computations. So it's not, in the view of efficiency, it's not really helpful. So we do a time-space multigrid currently. You can, depending on the problem you have, but if you have some parabolic equation, and this is parabolic here, you have some smoothing property. And you can, of the equation, and then you can exploit on that and really also cause some time space. It makes sense. There have been proofs early in the 80s by Hackbusch and others, yeah, for simple heat conduction equations. Yeah? But if you have such a equation, which is a parabolic equation, which finally has some smoothing property, yeah, then it makes sense to exploit this. And we did that. There are some papers. It's not yet in a state I would say we are at reached the solution, but the development is very promising. Yeah. So going away from parareal, which is appealing for the first view, but not the solution. This is clear. You introduce such an overhead of work. And then going to P-fast, they call it. This is finally a kind of space-time multigrid that you cause a time space. And then you can really use smoothing in time and go on. Yeah. Of course, this is limited. But the main thing still in all this still remains the spatial parallelization, since time is just one dimension.
Yeah, but in parallel.
Yeah, sure. You want to use everything. You want to use everything. Yeah, sure.
Well, I mean, how are you using waveform relaxation if you don't have a boundary value problem in time? Those are all for boundary value problems. Like if you do an IVP, what are you doing? The shooting method, or what is that?
In time.
Yeah.
In time, you just did the time discretization, the usual time stepping.
Right, but the way they do waveform relaxation, the multigrid in time, is they say I'm going from 0 to capital T. But if I have just some initial value problem, I don't do that. I don't know my capital T. So what are you doing?
Well, you're talking about ODEs or PDEs?
Does it matter?
Well, if you have PDEs, the main part of the work, computational work, is in the spatial part. Yeah? Provided you have more than 1D in space. Yeah? So this is what you have to parallelize. The time, you can include it if you have some initial and boundary value problems. Yeah? If you just have hyperbolic problems, the strategy is a bit different. Hyperbolic problems from the view of the solver are trivial, since you just need to sort it out in the right direction. Yeah? Then you walk in the right direction. But then everything changes. Yeah? Since you do not need a solver which is doing the heavy work and deciding on complexity. Yeah? So, but everything depends on your strategy how to march in the right direction. So discretization, which matters always, but it even gets a larger emphasis then. And then also the load balancing must somehow be done in the right direction. Otherwise, everything must follow the transport direction. If you go to merely hyperbolic problems, so mere initial value problems.
Other questions? Yes, please.
As you know, there is a lot of interest in core scale modeling, direct numerical simulations, for example, and for two-phase flow to liquids to fluids in a porous medium, it's very time-consuming. So people typically do just 100 pores or hundreds of pores, which is not enough.
Yeah.
How big can you go, or have you done that with
we didn't do pore scale
domain?
modeling.
How big the domain can be?
We didn't do pore scale modeling, since I still do not believe in resolving everything in detail. But if you are interested, we could have a break and I can talk about another problem, which is even farther away from your geophysics problem, but has a lot of ingredients which are interesting. And then we come to the point, how far can you go with multi-scale modeling? It's not that you just resolve the fine details. Yeah? You cannot do this all over. You would need a computer which is as large as the world. So that's what happens. Yeah?
Yeah, but that's what Dirac said also. He said we cannot solve them now.
Well,
as the computers get bigger, maybe it doesn't have to be that big.
What we do is approximately solving. And the main art is in the way of approximation. Do you get the physics out from the approximation or not? I just showed you such an example. Yeah? And you can get the physics out if you do it intelligently. Yeah? This is the message.
And the same actually applies to when you do molecular dynamics computation.
That's what you finally have to do. Connect.
How big can your domain or number of molecules be?
Well, molecular dynamics, there the problem is rather in the time stepping. You have femtoseconds. Yeah? In the space, you really can bridge this the spatial part. I can show you simulations where we come from the continuous level down to the resolving the size of the molecules. But the problem is in the time stepping. They have femtoseconds in their time steps and compute a lot of garbage, just stochastic variations, this molecule touches that and so on, which is not interesting on the scale we are looking for the solution. So the problem is always to how do we get from from this scale to the other scale. So finally, it's a multi-scale thing. So I would not advocate to do pore-scale modeling as such, but to use this as a kind of micro model inside a multi-scale model. Then it makes sense as a representative model.
Any more questions? Otherwise, I would like to ask one related to the program we're having here. So this is melt in the mantle. So the equations we're most interested in are essentially Stokes flow coupled with Darcy flow. So we have a deforming, creeping mantle and melt and going through it. So what would it actually take to solve those equations with the framework you presented? Is the implementation of these coupled equations something that can be done in a modular way, or would it be a major step of new development? How does it work?
Well, John, we had this discussion already, and you showed me some equations. Everything depends how complex the nonlinearities is in these equations, and how far this is. And I think there you have a zoo of choices. If you start with a simple problem, it could be done, say, in a PhD. It's a PhD work, typically. Not only the implementation, this is not so hard, but to do a educated simulation with that. For you run into so many things. Since I don't know who maybe he already did something in that area. So who did such detailed simulations? You get a lot of parameters. You may observe, as we did in this fracture business, we observed new effects. Nobody was able to tell us what was going on there, and you have to find out. So this is a PhD work, certainly. That's, I would say, the basis from which you should start, and then you can extend it.
It just seems to me that a lot of the properties of what you described would be quite suitable to our problems as well, so maybe it should definitely be something with a follow-up.
Yeah, I would love to.
So do we have any last questions? Otherwise, I'd suggest we'd break for coffee. We're quite a bit ahead of time, so we will reconvene at 11:30. So please do make use of the time and continue discussions over a cup of coffee. And let's thank Gabriel again.
Thank you.